And then I realized as I started having the opportunity to do so that I really like playing with data. I like looking for patterns in the data, looking for clues about what's going on with the data, like what the sort of fundamental truth is in the data that I have about the universe. And I also like working with computers. And again, as I had more and more opportunity to work with advanced technology and cutting edge computing architectures, I realized that this is a thing that I really enjoyed. Figuring out the best way to use the hardware that I have available to answer the questions that I really care about. But these are not the only things that have kind of driven what I'm wanting to do in my career. I also want very much to be doing something that has some kind of positive impact in the world. And I don't mean that in sort of a generalized sort of hand-wavy way. There are some things that I think are really pressing questions that we have as a society. And for me, climate change is one of the most pressing questions. Understanding that and understanding what we can do to change that, that's important to me. But also, I have I think that understanding how the universe works as a whole is something that can have a positive impact on humanity. I'm slightly idealistic in that sense. I do think that science is generally speaking a good thing. And so the choices that I've made in where I've gone with my career have been kind of driven by this. Where do I think I can have an impact and have a positive impact in the things that I care about? And also importantly, and I would say equally importantly, is this: I want to live somewhere I want to live. I want to live somewhere I enjoy, whether I can do the things that I want to do, where there are people that I enjoy spending time with, where the climate is something that I can tolerate. This is, and I make this point here because when you're thinking about what you want to do, where you want to go to college, like what you want to, where you want to end up in your life, the location is actually also a factor that's worth considering at the same level as what your career ambitions might be. Factors outside of simply work and career are also really worth taking into consideration and weighting appropriately. And for me, this is a big deal. I've turned down jobs, very good jobs, because they're in locations that I did not want to be. And for me, that's really important. I want to live somewhere fun. And that's been also a driving factor in my life. And it's one of the reasons why I live now in the San Francisco Bay Area. I think it's a great place to live. All right, so let's go through a whistle-stop tour of what I've done in my career. So I think most people on this call are from or around the Bay Area. I wonder how many people knew that there's a particle physics experiment that was running in the San Francisco Bay Area. I see some nodding heads, yeah. So the Large Hadron Collider at CERN in Switzerland is by far the most famous particle physics experiment in the world. But before there was the Large Hadron Collider, there was the Babar experiment that was running at SLAC National Accelerator Lab, which is at just northwest of Stanford University. So this is the layout of the accelerator, and you can see the 280 freeway running right underneath it, in fact, underneath the accelerator there. So this was an particle physics experiment that was running up until about 2004, thereabouts, 2005, when funding went away for it. But this was an experiment that I was working on when I was in grad school. So I did an undergraduate degree in physics and French, and I was really interested in particle physics, although I knew very little about it. So I went to grad school to work on this experiment, and I went to grad school in Edinburgh in the UK, but particle physics typically has really large collaborations. And so the group I was working with was part of this collaboration, and so I came over to California to work on this experiment and understand something about the nature of matter. So the big question that we were looking at is, what's the difference between matter and antimatter? And so this experiment was creating matter and antimatter. And in the big detector, we were looking at the behavior of antimatter and seeing if this was any different from regular matter. And this is kind of where I started getting really interested in computing and data analysis and data analytics, and also machine learning. So machine learning has been used in the particle physics community to analyze data for decades now. It's really been, particle physics was pioneering the use of machine learning to analyze data, because it's a field that has vast quantities of data. And machine learning is very effective, as you've heard in the previous speaker. Machine learning is very effective in being able to analyze a lot of data and pick out patterns. So that was also where I started getting interested in machine learning and using it for physics. So I worked on this experiment in particle physics after I went to grad school for 3 years or so. I did a postdoctoral research fellowship working on it. And then towards the end of that time, I started to get interested in understanding the nature of matter in a slightly different context. And so I started to get interested in cosmology as a way of understanding the nature of the universe. And cosmology is really looking at the universe from a completely different scale. So as particle physics is looking at the fundamental constituents of matter, subatomic particles, cosmology is looking at the entire universe and trying to understand what's in it and what are the rules that govern motion of objects in the universe, the evolution of the universe. How does time work? How does gravity work? And so it's coming at the same kind of fundamental questions about the nature of the universe, but from a very different scale, the very largest scale. But the data analysis was actually surprisingly similar. The universe is a big place. If you have a big telescope like the Rubin Observatory that I was working on, this is a picture of it under construction. It's down in Chile. It's still under construction, in fact. But if you work with the big telescope, they have a lot of data, a lot of image data. It's a big digital camera pointing at the sky. It takes a lot of pictures. You have a lot of data that you need to analyze, and you're looking for statistical fluctuations in that data. So it's a very similar kind of analysis. You have a big data set, you're looking for patterns in it. And the way you interpret those patterns is a little different, but it's actually a very similar skill set to working in particle physics. And so this is what I was doing. I worked on running simulations, so running model universes and running simulations of the telescope, working on new algorithms and machine learning algorithms in particular, again, for detecting patterns in the structure of the universe. And this is also where I started to get interested in advanced computing architecture. So I started using GPUs, which are graphical processing units, for data analysis. So if anyone's unfamiliar with a GPU, it is the graphics card, basically the graphics card that you have in every computer. You have a little graphics card in your phone as well, a small powered one. But if you have a very powerful graphics card that is optimized, say, for rendering images for computer games, they have to make calculations, a lot of calculations very quickly. And this can be very useful for scientific data analysis. If you have a large amount of data that you need to perform the same calculation on all that data, GPUs are actually perfectly optimized for that. And so when I started looking into this, this is just when NVIDIA, which is the main GPU technology company, they just started pivoting away from marketing towards purely gaming and towards general computing. So this was when we started having GPUs, general purpose GPUs. And it wasn't, in fact, until a couple of years after this that NVIDIA realized how useful GPUs would be for machine learning. And now this is by far their biggest customer base. NVIDIA is really very smart in how they picked up on these market trends and pivoted very quickly. But GPUs are now the bedrock of how we do nearly all our machine learning training in academia and in industry. And I'm happy to talk a little bit more about that if anyone's interested later. But this is where I first got interested in using novel computer hardware in order to do data processing. And eventually this brought me to working where I work now, which is Lawrence Berkeley National Lab at the Supercomputing Center there. So I work at NERSC. And NERSC is the National Energy Research Scientific Computing Center. It's the Mission High Performance Computing and Data Center for the Department of Energy Office of Science Research. So if anyone's unfamiliar with the Department of Energy Office of Science, it's actually the largest funding agency for scientific research in the US. It funds tens of thousands of scientists and I think something like 28 big user facilities, which are big experiments and big computers that scientists can use to support their research. And NERSC is one of their big computing centers. And we have a lot of scientists that use our systems, something like 8,000 users every year working on 800 different projects. And we support all different kinds of computing that people want to do there. Large scale modeling and simulations, theoretical simulations, modeling of climate, different climate scenarios, modeling of different materials, modeling, for example, of different proteins that could be used to combat COVID-19. That's something we've been doing a lot of in the last year. And we also do a lot of support for data analysis from other Department of Energy facilities, which is, of course, what my background is in analyzing data from experiments. And so that's the area that I work in. I lead a team who supports data analysis for experimental scientists coming in to work with our systems. So I want to say a word about the system that we have on the floor at the moment. So this is Cori. If you can make out from this image, you can see that there are something like 7 or 8 rows of supercomputer here. This is a massive system. When we first launched Cori, which was in 2016. This was the 5th most powerful computer on the planet. But in the last 4 years, things have moved on. We're now only the 20th most powerful computer on the planet, but it still does excellent work. We name all our scientists after, we name all our computers after scientists. And Cori is named after Gertie Cori, who is the first American woman to win a Nobel Prize in, I think it was chemistry and physiology. She has discovered the Cori ester, which regulates insulin production in the body. And so we do quite a lot of biomedical simulation and data analysis work. So it was appropriate for us to choose Cori to name our system after. So what I do at NERSC is, there's a variety of things that I do here. So for example, I work on machine learning for cosmology. We have a very big computer system. We have a lot of data on our storage, in our storage systems. And so we can do some really advanced machine learning for scientific purposes. And part of what my job is to make sure that scientists can use our systems for the things they want to do. And they want to do machine learning. So part of my job is to make sure that we have the right software available for them, and that software works, and that software works at large scale, at supercomputing scale. So to do that, of course, I have to be able to do it myself and test it out and run big challenges. So big challenges is very much part of what we do at NERSC as well. I've led 2 Gordon Bell submissions, and these are submissions for a Gordon Bell Prize, which is an award given to innovative use of supercomputers. And we've made many Gordon Bell submissions at NERSC, and really we do that to push the architecture and push the way that scientists can use that architecture, the computing architecture, and to make sure that scientists can do what they need to do at the scale they need to do it on our systems. It's a good way for us to test our systems and to test ourselves as well. And another thing that I want to mention that I've been leading is I lead something called the Super Facility Project. And this is something that we've been developing at Berkeley Lab in the last 5 years or so. It is an acknowledgement that experimental science is producing more and more data. All these different instruments, these different telescopes, light sources, fusion reactors, electron microscopes, genomics machines and systems, they're producing more and more data. And in order to be able to analyze that data, a lot of these scientists need to use large-scale computing facilities like NERSC. And so the super facility project is this concept of connecting facilities. So connecting the experiment facility with a computing facility via a high-speed network in order to be able to get the data from the experiment to the computing center and analyze that data really quickly. So the scientist doesn't have to wait around for weeks after they've taken their data to get their results. We want them to be able to get the results really quickly. And so that's where supercomputing comes in. We can really help with that. So that's something that, again, my background's in experimental science, is something that I've been able to work on. And it's really, I got to say, it's one of the most fun parts of my job, is that I get to work with a lot of different scientists who work on all different kinds of experiments that I'd never heard of before I came to NERSC. And so it's kind of expanded my horizons, my scientific horizons, like being able to work with people who work with like plasma fusion experiments, like trying to develop the next generation of clean energy sources and that kind of thing. I think it's really cool. I've really been able to enjoy working with different science teams through this. All right. I think the last sort of technical thing about my job that I want to point out is coming back around to GPUs and using GPUs for science. So I mentioned Cori, which is the supercomputer we have on the floor at the moment. We are in the process right now of installing our next generation supercomputer. And this is a system called Pearlmutter. This is named after Saul Pearlmutter, who's a cosmologist. In fact, he and his team won the Nobel Prize for physics 15 years ago now for the discovery of dark energy, which is something that I spent time studying. And so it's kind of a neat synergy, like everything's kind of come together with this system. For me personally, you know, it's complete coincidence, but it's been kind of fun. So Pearlmutter is a system that is contains GPUs. So this is the first system we've had at NERSC that is based around GPUs. And so we will be having NVIDIA A100 GPUs. It's the latest and greatest GPUs out of NVIDIA. And we're using AMD CPUs, the Milan model, which I think has not yet been released. And there are a number of other architectural features that I think are really fun, that's going to be great for doing data analysis for our scientists. And one that is, I think, really interesting and new, this is a little bit like computer hardware nerd, but we will have the very first all-flash scratch file system. Now, to most people, this isn't that revolutionary. Like, not many people have spinning disks for their file systems, for their storage, right? Like in everything we have SSDs or flash drives. Like there's very, very few places where in your home computer you'd use spinning disk for storage. But for supercomputing, spinning disk is still the norm. It's still the standard. That's mainly because we need so much storage on a supercomputer. You know, we're talking tens of petabytes, maybe even hundreds of petabytes of storage. Buying SSDs for that much capacity is just too expensive. Like, we just can't afford it. And so we end up, getting spinning disk for our storage systems. This will be the first time anyone's been able to afford an SSD or flash-based large file system. So it's going to be really fun. The performance of an SSD file system is so much better, and particularly for things like machine learning. When you're doing machine learning, you're constantly reading a lot of data from disk, and this is going to really help make machine learning applications go much faster on our system. So I'm excited about this. This will be coming online in about 3 months. It takes a while to integrate the system and kind of do the testing, but we're going to start get to play with it in the start of next year, which is going to be fun. All right, so the last thing that I wanted to sort of summarize with is going back to this theme of moving careers and shifting between different career paths. I've held the jobs I've had, I'm not obviously qualified for. I took particle physics as a PhD, despite having never taken a class in particle physics. I was just interested in it. I worked in cosmology, and I taught astronomy at Stanford University, by the way, without having ever studied astronomy before. I was basically self-taught for that. And now I'm a group lead at NERSC, but I've never really taken a class in computing before. But I think the point that I want to make here is that you don't need to have formal training in something in order to be good at it. The sort of general skills that I have in that I've developed in communication, in data analysis, and in computing have really enabled me to move between different areas in my career. So I've really, the theme that is sort of pulls everything together in my career is using computing to enhance experimental physics. And because I've spent a lot of time doing this, I've got experience in this, I'm able to apply that skill set to different areas. And it's something that I'm really passionate about. I think I think if you have access to advanced computing hardware, then you can answer new and harder questions about science. And I think that's just really important. And yeah, the skills that I've developed in doing this have enabled me to move between these different fields, even if I'm not sort of obviously qualified for them. And that's sort of the meta point that I want to bring out is that if you, as you go through, high school, college life, look out for opportunities to develop these kind of skills that you can apply to different areas. Because if you want to switch career or switch subject direction, you can bring quite a rich skill set to a new area without, even if you don't have direct experience in it. And in my experience, that is something that hiring managers really respond to. And yeah, it's okay if you change your mind, if you decide you want to do something else. I've done it a few times and it's worked out pretty well for me. I'm doing some work that I really love. And that's, I think, perhaps the most important thing about thinking about what you want to be doing is what do you make your decisions based on what makes your whole life better, not just, don't optimize too hard on one small part of it. Think about all these factors when you're thinking about where you want to go to college, what kind of college you want to go to, what kind of career direction you want to take yourself in. It's worth spending your life doing something you're passionate about, even if that changes. All right, that was all the material I had. I hope there'll be some questions for me.
Yeah, there are plenty of questions, and
okay,
why don't we get started? So what was the most interesting scientific endeavor you've helped with through NERSC?
Ooh, through NERSC?
Yeah.
Okay, so the most interesting one is nearly always the thing that I'm working on now because I'm like excited about it now. Right now, I'm working with an experiment called CMB-S4, which is a jumble of numbers and letters, but it's an experiment that's looking at the cosmic microwave background. And so this is a cosmology experiment. So, I love cosmology. But the reason why this is cool is that they've got two main telescopes and a bunch of smaller ones. But one telescope is at the South Pole and the other is in the middle of the Atacama Desert. And these are very far away from anything, very far away from high-speed internet, very far away from any way to get data from the telescope to NERSC easily. And it's a really fun challenge. Like, how are we going to get petabytes of data from the South Pole to NERSC? At the moment, the plan is to write them all on massive hard drives and then get a helicopter to come and pick them up and take them to us physically. But we're also thinking about, is there a satellite? Can we use a satellite to beam the data to a satellite and then have that go to the mainland? It's a really fun challenge.
Yeah, that's
I think that's cool.
Oh, there were so many. Okay, is there such a thing as anti-dark matter? That's more astronomy based, but
that is yeah. The answer to that is we have no idea. So dark matter,
like a lot of things.
Yeah, that's one of the reasons why it's interesting. We don't know what dark matter is. So when you talk about matter and you have antimatter, the difference between matter and antimatter is the electrical charge. So, an electron is matter that has a negative charge. The identical particle with a positive charge is a positron, and that's the antimatter equivalent to the electron. So to the best of our knowledge, dark matter does not have an electrical charge. And the reason we think that is because it's dark. it doesn't interact with light, which means it doesn't interact with the electromagnetic spectrum, which means it has no electric charge. So to the best of our knowledge, we don't think, we think that dark matter is neutral and therefore, doesn't have an obvious antimatter equivalent. Although if it's a certain we don't know what dark matter is, but it might be that it has an antimatter equivalent that doesn't have an electrical charge, but like has different, substructure that sort of makes it a separate antiparticle rather than it being its own antiparticle. It gets complicated, but the short answer is we don't know, because we don't know what dark matter is, but it's unlikely.
Yeah. Okay. So this is interesting. Can you use the cosmology data that you collect to make predictions about like astronomy, and have you done so?
This is an interesting. That's a very subtle question. So in general, cosmology is an observational science, right? We can't do experiments with cosmology, not easily, because we can't do a lot to affect the universe, like how we normally design an experiment in for other areas. So in cosmology, it's really about looking at the universe and seeing if it agrees with your predictions. And your predictions generally come from a theoretical simulation, or from someone like writing down a theory, like there's the equations of it. So we typically don't use data in order to make predictions about the universe. We use a simulation or a model or a theoretical model to make a prediction. And then we compare that model with the real data to see if they match or not. That's kind of the simplest way of explaining it. So I've never used real data, like observational data, to make a prediction, but I've used theoretical models to make predictions about the universe and about what I would see in the data, and it has matched. So I've not made any like groundbreaking, like surprising discoveries in that. What I was able to observe matched what the predictions were, which is confirming that we have a pretty reliable model of the universe at the moment.
Wow, yeah, and I never knew there was such like a huge intersection between computation and lots of like these scientific fields. They were always so separate to me in my mind, but yeah, this is incredible. So what was your favorite topic to research about in cosmology, and how did you use machine learning to when you were studying it?
Okay, so my favorite topic in cosmology was the phenomenon called gravitational lensing. So to explain this, briefly, this is something that Einstein predicted, by the way, because Einstein really did know everything, it seems, about cosmology. So light, travels in a straight line. So you would think, if light traveled around corners, life would be very different for us. But light travels in a straight line, except when it's going through a large gravitational potential. And then light gets deflected. This is because space-time is curved around very massive objects like stars, like galaxies, like collections of dark matter, that warps space-time such that light no longer travels in a straight line, but it gets deflected. And that is known as gravitational lensing, because it's like the gravity is acting as a lens for the light path. And so what this means is that you, when you look through a telescope, you see distortions in the shape of a galaxy. Instead of a galaxy looking nice and round, it might look bent, like a banana kind of shape. And so that was my favorite thing, because it would just have you'd see really weird things going on with that. And I just thought it was quite cool that like gravity bends light. It's a good concept. For using machine learning, actually, I was using machine learning to answer a really basic question about the observations I had, the data I had, the images that I had, coming off the digital camera on the telescope. Is that here's a speck of light. Is that a star or is it a galaxy? It's actually a really hard question, because when you have a very faint star, it looks very much like a very faint galaxy. And it's very hard to tell the difference. And so machine learning is a very promising way to distinguish between stars and galaxies when you're looking at images. And that helped.
Yeah. Oh, and there's a bit of a shift in focus here. But
Yeah.
for high school students, so what are some opportunities or just general advice you have for high school students looking to be involved in engineering and technology?
I mean, I know this is perhaps obvious advice, but I can't state it strongly enough. Know how to code, know how to use computers,
Right.
know how to write code. Computing is in everything, like even, you know, the most hands-on kind of engineering, even the most esoteric type of science. Computing is in everything, and if you can't code or know how to analyze data or handle data, then you're going to struggle. Or you're going to have to do what I do, which is learn on the job, and that's really it's a bit painful. So computing is an obvious, perhaps an obvious one, but it's really essential. And the other advice is internships. If you have an opportunity to do internships of any kind, then take that. Take the opportunity, and especially in summer internships or part-time projects that you can do. It's useful not just to get experience, you know, it looks good on a CV and all that on your college applications, but it's the only way you'll really know if you like doing this. Studying something in college is not the same as having some hands-on experience with it. So this is very much for me when I work with interns. I have a lot of summer interns, and a lot of the point of the internship, you know, there's a good project, we're doing something useful and interesting, but I want the intern to figure out if they enjoy it or not, if they want to go into research, if they want to go into research computing, because there's not much point in continuing on a set career path if it's actually not something you like all that much. And the reality of doing, you know, engineering or doing research or doing science as a job, not quite the same as you might imagine. It's often really boring because a lot of work it can be very hands-on and repetitive. And so having any opportunity to try that out yourself and see if it really is, you know, is it something you really want to do, that's important.
Yeah, the hunt for opportunities is something I think a lot of high schoolers are really trying to focus on and struggling with. So this is incredible. Oh, okay. So what advice or okay, how do you keep up to date with developments in your field, which I'm sure are like coming in at rapid paces, especially in astronomy and such?
I'll be honest. I do a really poor job of that. So and honestly, I use social media quite a lot for this because I know a lot of people I know a lot of astronomers, I know a lot of computer scientists. And so just like seeing the things that they're posting about, like, oh, I saw this cool news story, or oh, I just read this really interesting paper. That's kind of like a filtering system for me that like filters a lot of the interesting stuff that other people have done the hard work to figure out. So honestly, I sort of rely on other people I know to point out things that are interesting and cool that are happening, because yeah, things do move really quickly, and I often don't have the time to sift through it all myself. But the other thing that I do, like make the effort to do, is go to conferences. And you know, in research, that's very much you know, a lot of how you can keep up with things is you go to a conference, you see what the talks are, see what the hot topics are, what are people buzzing around. You sort of get a good feel for what's important, what's new from that. As a you know, in high school, a good thing that if you don't have access to industry conferences, which you probably don't, there's a lot of good industry-based or you know, subject-focused blogs out there. And you know, online magazines that do a really good job of summarizing sort of what's new and what's important, and you know, interesting results that are coming out at a level that it cuts out all the less important stuff, all the noise.
Yeah, that sounds like great advice for not just high schoolers, but middle schoolers too, anyone who wants to like keep up to date with any sort of like science or interest. Okay, so what safeguards do you use to avoid mistakes? whether it's just general in the industry or specific to your work?
Ooh, that's a really good question. First of all, we make a lot of mistakes. It's part of learning, and it's part of research. And in fact, it's explicitly, you're expected to fail. If you're in an area like research, or if you're doing something that's kind of pushing the boundaries a bit, you expect to fail, and that's not necessarily a mistake. Just sometimes things don't pan out. Usually things don't pan out, and so uh, understanding that and accepting that something fails, it doesn't mean it was wrong or a mistake. That's sort of a mindset that you have to learn a little bit. But to avoid like making a real mistake, like say, I don't know, like accidentally uploading a virus to our supercomputer and like cause, our $120 million supercomputer and like turning it to slag, like that would be a problem. We have a lot of safeguards. We build in a lot of safeguards around this. Data, we always back up your data. Always back up your data. In multiple locations. I've certainly accidentally deleted like vital research data, and I've lost like days of work, but I've had backups that I can access, so I've only lost days of work, not months of work, that kind of thing. So that's on the computing side. On the sort of looking at data and coming to conclusions side of things, there's nothing better than talking about what you're doing with a colleague or with a friend or with someone who's interested in it. And that's a really good way of avoiding mistakes and avoiding kind of going down a wrong track, is just sharing, like chatting about it casually, like, oh, I'm doing this, it's really cool. And someone go, really, you're doing that? Have you thought of this? And then you sort of get a whole new perspective on it. And that's something I really like. I really like working in collaboration with other scientists, with other experts, with my colleagues, because I get that perspective. And so we're not that secretive in science. There's sort of a bit of a myth that like scientists just work on their own and they don't let anyone see their results because they're scared of like people stealing the results or something like that. And in general, that's not true at all. Like, we want to be able to share what we're doing to avoid making mistakes, to get other people's opinions and perspectives on what we're doing.
Yeah, so I guess it's already 5:30 and I guess we don't have a lot more time for questions. So we're going to have to wrap this up here. But thank you guys all for coming. And Miss Debbie, Miss Bard, I don't know. But do you have any closing statements you want to share to all of our listeners, watchers?
Words of wisdom? No, not really. The only thing I've got really is to find something you're passionate about and run with it. You can put up with a lot of very boring and frustrating days at the office if you're passionate about what you're doing.
Yeah, that's, I guess, old advice, but I guess it's still true always. So yeah. Thank you everyone for coming to this session. Tomorrow will be engineering with some very qualified speakers, and I'm sure you'll love that just as much as this. So everyone, thank you all, and remember that if you have any other questions or concerns, or if you want to, I guess, ask anything else to Miss Bard, please email us at ch_Fremont@superposition.tech, and we will try our best to reach out to her. So I guess that's it for today. Thank you.
Thanks for having me. Thanks for having me, everyone. It's great talking to you all.